So I'm on a roll. Figured I would just finish out this week with providing you guys the videos. This one I would like for you to give me some feedback. So if you've never seen these videos before and you're like, why is this required? I just want to know if these are helpful to you, if you watch them, what I could be doing better, if you want me, and take it as serious for learning, not necessarily like, well, just show us the answers and pause. Show us the answers and pause. That's not going to happen, right? You can try and click through all you want, but remember, my goal is for that learning and that wonderful understanding. And most of you, that's your goal too. And it's fun to understand. So how can I help you learn, understand, make these videos more applicable? Maybe do practice problems differently, maybe a bigger whiteboard, a clearer whiteboard that's not so messy, things like that. Any suggestion you can think of. And if you have none, that's fine too. Just kind of wanted to touch base on the usefulness of these videos for you in our course and try to improve them, try to make them better. And if you're like, just get to the point and stop rambling, well, that's a lifelong battle that Mrs. Reynolds has been since I was a child. So, domain and range. So these are big ideas. Hopefully by now that's starting to sink in. The domain is just the values that we can put into our function. Functions can be wild. We're going to talk about piecewise functions. We have the sine functions, radical functions, all this stuff. We discovered there's holes in graphs, little tiny invisible holes that we would never see if Desmos didn't tell us about it. And domain, X values that can go in. Typically it's X. We say domain and range because we change the variable sometimes. Sometimes it's T. All right. The domain is the input, typically X, but for a general sense, input. What is the input that's okay for it to go in here? Well, you're like, wait a minute. You can't have a negative square root. That's true. You can't. But we're talking about all radical functions. And a radical function is something that has a rational exponent. What? Rational functions? Radical functions? I know. So let's break it down. For those of you who are like, I understand. Excellent. The fluency is important. When I say a rational exponent, in your mind, you should think, I have a variable, and the power is in the form A over B, where B is not 0, and I think it needs to be positive. Well, if we can think about that later. Basically, I want it to always be a rational, and if B was, B is negative would be fine. Wait a minute, if it was, that wouldn't matter. Just B can't be 0, and these need to be, A and B need to be integers, so whole numbers. Could it be irrational? Is this I'll look this up again. But anyway, I always have these other definitions questions to clarify for myself as well, because I have the generic definition. But then I start to think, well, what about this function? What about this function? And that's just me on my tangent because I love this subject. So here we go. X, the cube root of X plus 2 is how we read this. This is now, how would this look? If we have, is this one where it looks like this? Something like that. Because we have these, this is X cubed. So now what does the cube root look like? I gotta go graph it because I'm trying to, you could either plot it, some points, and try to look at it or whatnot. But anyway, let's get going. We just need to know about domain restrictions and range restrictions. Obviously the answer is there are none. It can go to negative infinity to positive infinity for input, which is true because we can find the cube root of negative numbers. The cube root of negative 27 is the same as negative 27 raised to the 1/3 power. What these notation is asking, they're asking for some number that when we multiply it 3 times by itself, so inside this blank, out pops negative 27. There is indeed positive and negative numbers. So we can have negatives as an input for our domain for odd radical functions. Okay? 1/3. If the denominator in simplest form, man, there's so many different things, is odd, then they exist. Okay? So here we would have -3. This example would show us -3 times -3 is positive 9 times -3 would get us to -27. So that's why the input, because that 3 is odd, can be absolutely any value of x. It's fine. And then the output is going to be any value of x. This one I am going to graph it because I want to talk to you about how you graph those. In first semester, we rewrote them with a rational exponent with a denominator, the root. We call that a cube root. And you need to remember that is now the denominator of the exponent. Okay? So I don't know if they have the symbol cube root. We can look. No. So what's this? I don't know. So now you need to be able to write it as x to the power a to the b, or you could use the shift 6. Either one, it's going to do the same thing, okay? A to the b. I think we can do 1 divided by 3. It'll work. So you didn't have to use parentheses. That is the same thing. There it is. See? I was trying to draw that. Okay? Because we can have all these negative values of x. It's different than the square root of x, which will just be this half over here, like about that half. Ready? See? Blue. Just the blue side. Because that domain, no, we can't put any negative. Look, there's nothing. We cannot put any negative numbers in there. And then therefore the range, it's not going to outspit any negative numbers. Got it? It's just going to put out positive y values and positive x values go in. So the domain and range is different for an even. This is the same. Watch, x to the power of 1/2. There's the green. The green and the blue are exactly the same. Let me turn this one off so you can see. Blue, green, just notationally different because there's an invisible 2, it's the only invisible 2 I know of so far, outside this radical symbol, which implies the root, this is the square root 2, would be the denominator of the new function. If this was x, say, cubed, let me raise it to the power of 3. If I want to get that matching graph, this power would be in the numerator, so we would change that to 3 to get the matching graph. We talked about this. It's a little bit of review. Let's go back to let's go back. I can help you with this. It's fluency in notation and definition. Learning a new language, which is great for your brain. Learning a new language, it's very important. All right. For this one, our input, our output are infinite. So that should be fine for all of them. That was a question. Oh, I see. That's fine. It's probably going to be the same. They're all cube roots. So yeah. And when in doubt, you can come graph it, right? You can come graph it. So how would you graph that one that had something inside the radical? Hey, no, I need parentheses. So you got to mess with parentheses. How would we graph? This is important skill. So let me put a parenthesis here. Haha, there's my parenthesis. I'll put this parenthesis over there. -2. I gotta turn it on. Oops. See? So see how there's nothing wrong. We have to be careful about holes and whatnot, but thinking about what we can and can't put in these functions, it's fine. So, okay. But that's how you would write the cube root of something underneath the radical. That's important. Let me see that. What's this one? See, there's this underneath the radical. So the root is the denominator. Then you need to put this in parentheses and then the power up. Then you could see, oh, look, it's going to, all the x's, all the y's, even though that's going to reach the y's very slowly. Let me zoom out. It's, it looks like, wow, it does look like it's never going to reach it. But we're getting really, 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 really big. Wow, that's interesting. I don't know. That's interesting. All right. Why is there not horizontal asymptotes? It really looks like there should be, huh? But that's what we can't always trust the visual. What are the domain and range of this function? Okay, this is the standard square root function. You can graph it, or we can just think about it. So feel free to graph that. This symbol is in Desmos, right? This is in Desmos. Reload. So you can do that exact thing if you wanted. Right, here it is. You could type in -4 square root of x. There you have it. -4 square root of x using this down here. Wow, all right. So then just looking at this graph right here, not zooming, not nothing, where is it? What values do you see? I see only positive x values. Nothing is over here, right? No negative x values. Can it be 0? Sure. There it is. We can click on it. If you can click on it, then it equals. If you've ever seen me click around and it's not equaling, then that means it's not there. We can't click on it, or we need some sort of point of intersection, because Desmos won't just let you click on the points and keep them there unless they intersect. It's good programming for exploring. It's really good programming. So, okay, what about the output? So the domain, I only see, and the domain is your x values, so your left and your right. So if you only see 0 and over here, I'd say your domain is x greater than or equal to 0. If it's an interval notation, it should be a bracket, 0, comma, positive infinity, parenthesis. Well, look, I don't know. The output, now, what do you see? What y values do you see up and down? Well, I don't see any up here, so I see no positive y values, and that's this little negative right here. That's what's going on right there. If this regular, right, that part is regularly over here, only positive, you add a negative, well, now it's going to be only negative. Because we can't get this to be negative, and a negative times a negative makes it a positive, so that's what's happening. Anyway, so our output, y less than or equal to 0. So our range, the y values, the output values, so they're both, no, they're different. So x would be 0 and greater than, so I don't know how they're going to, let's go talk about the notation. Let's just go look. There it is. Okay, perfect. See this square bracket? That includes 0 because it can equal 0. X can equal 0. We can take the square root of 0, it's 0. It can't ever reach infinity or negative infinity. So range, it's going to come up, see negative infinity up to 0, which is why the negative infinity is first, comma, up to 0, right? And it includes 0 because y will equal 0. 0, 0 is a valid input-output. So that's what's going on here. What are your other variations? Let's just take a quick peek, see if there's anything I'm missing. Nope. Nope. Okay. Graph it, think about it, input, output. Which graph represents the function? All right, so I don't think you can copy paste this, but let's try it. Let's see what happens if you copy paste this function into Desmos. I don't know if it'll register it. It doesn't. That's wild. Absolutely wild, but you can fix it, right? We can fix it. We can get rid of all whatever this is going on. I'm going to take this. I'm highlighting it. I'm going to hit Control X because it cuts it. I'm going to click inside and hit Control V because it pastes it. There it is. Well, look at this beautiful graph. What's happening here? We've got a vertical shift, right? Because remember, this was down here when we first, the regular parent function of x squared, of the square root of x, was just down here and up. So now we're going to vertical shift it up 1. This inside, remember we didn't talk about it with sine functions because of the phase shift, but for radical functions, it's a horizontal shift. If it's a -1, then we shift it over to +1. So kind of the opposite. You could read it like that, or you can just kind of remember, if it's a negative, I'm going to shift right. If it's a positive, I'm going to shift left. Up to you how you want to think of it, and always use technology to help you think. So look, it goes over 1, up 1. That's fine. Right 1, up 1. Hey, right 1, up 1. Nope, that's back 1, up 1. That's right one, down one, and that is back one, down one, left and down one, right? I downloaded a PowerPoint and I'll have to blur that out because I can't share. I have to see if it shared student information. I loved seeing it. I love seeing it, but I can't release it out there on a video like this. Look, horizontal translation, left. If it's plus, we go left. If it's minus, we go right. Here's what's happening. Plus and minus D. If it's plus, we go up. If it's minus, we go down. That one's kind of nice. Vertical is just directly up, directly down. Horizontal is left, right. Okie dokie. Ooh, question 4. Which graph represents the function? You can always graph it too, which we did. Cube root. The denominator is 3. There's no power in here, so it's just 1/3. In order to graph this, you would need to type x minus 2 raised to the 1/3 power. Then you could see the graph in Desmos. Okay? For me, let's talk about it. If we had remember I was saying, okay, well, the regular cubic function looks something like this, so the cube root has to look something like this. So I know it's a cube root, and oops. I know, hold on. It should, if this is my axis, and here's the origin, it should come through the origin and be good. This is a horizontal shift. If it's negative, it's a shift right. So I argue that I will shift right 2, and I will now have it come down through there like that. So that's what I argue all I'm looking for is my shift, because I know what the parent function looks like. So instead of coming through the origin, it should cross at 2, 2, 0. A shift right, because that's a negative, so we do the opposite. Horizontal is the opposite. Vertical is exactly what you see. Negative is down, positive is up. Horizontal, if it's negative, we go right. If it's positive, we go left. Let's go see. Yes, there it is. See, whoa. Not up. Nope. That'd be if it's on the outside of the radical symbol. And not left, and not down, outside. This vertical up and down is when it's outside of this radical symbol. And when it's inside, it's a horizontal. What's on the outside, it's up and down. And then if it's on the outside with multiplication, it changes, right? Vertical shift. Okay, good work. That's 4. Let's go into 5. Each transformation performed. Okay, that's exactly, all right. These are the words the compression and the stretch, I fight what they imply. So students, if you have the answer, help me out. I learn from you guys all of the time. It's one of those things that I don't like 5 plus 7 doesn't equal 13, but it's kind of in there. And I always have to be like, oh, no, that's not right. And 5 plus 8 doesn't equal 12. I don't know why I do that. Anyway, I haven't switched in my mind, but I'm aware of it, so I pay attention. Which transformations have been performed on the graph f of x equals 3 cube root of x? So that's our parent function. To obtain the graph g of x, so now a new function, negative 2, 3. Oh, this is lovely. Okay, this one I can do. These are the... It's when we start messing with this guy that gets me frustrated. When it's on the outside, I got... let's just see. Let's see. Maybe I can. It might be negative 2. That negative on the outside, not on the inside. See, not under the radical. That's what I mean by outside, inside. Is a reflection over the x-axis. If it was on the inside, it'd be a reflection over the y-axis, and that changes things. It changes things. I'll show you in a second. -1, that's a vertical shift. We know this much. I know that's a vertical shift. Down 1. Down 1. So we got the reflection, we got the vertical shift. This 2. That 2 is going to be a vertical compression or stretch, and that's where the words get to me. For me, this should be a vertical stretch by a factor of 2. Meaning if this is our normal graph, oh wait, we have like a squiggly one, right? We're stretching it up by a factor of 2. Let's go see. Okay, stretch away from the x-axis. Yes, we're stretching it up. So if this is the x-axis, we're pulling it away from the x-axis. We reflect, we stretch. So it's stretch, not a compress. That's good. Translate, nope. So they might say translate down. Translate the graph down. Okay? So sometimes they said vertical shift. Now they're saying translate. All of that stuff is got to be interchangeable, just like hi, hello, how are you? That type of thing. Good work. Let me see if there's any others that are kind of tricky. Okay, this is 1/4. What I want to show you here, this might help you. This is what I'm thinking about. A vertical stretch, because the absolute value of that factor is greater than 0. But if it's, shouldn't that be greater than 1? I gotta look this up. I can't believe I just noticed that. But if it's a vertical compression, it will be between 0 and 1. And notice it's absolute value, because if we introduce negatives, then it's a reflection. So we just take the absolute value to think about how before the negative, how is it affected with a stretch and a compression. So this should be a vertical compression or compression towards the x-axis, depending on what they like, right? Translation, perfect. They say it right here. Excellent. Up, down, left, right. Reflection, stretch, compression, stretch, compression. These two are usually the ones that I have to think about it. And then the horizontal even more. It really, this one I have to be like, what? Compressed by a factor of 2 or compressed by a factor of 1/2, right? Stretched by a factor of 2 or stretched by a factor of 1/2. Anyway, in my mind, if it's horizontal compression, then we have by a factor of 2, you keep it positive. Right? If it's a horizontal stretch, we use the fractions in there. But I need to check this again about this one. All right, back to our quiz. We have now, this should be a compression towards the x-axis, because it's a vertical compression, because 1/4 is between 0 and 1. We have a shift up, translated up 6 units, translated left, because that's a plus 3. Look. Plus x plus c, horizontal translation left. Minus or plus translation up. Here's your reflections. And then now it's this, let's go see. Your guess is as good as mine. No, because there's no negative. Stretch away, compress closer to the x-axis. Go back. Let's double check. That's what we said, I think, right here. Vertical compression, because that A, that multiplier, the factor, 1/4 is between 0 and 1. Okay. All right. Hopefully that's helping, and it's helping me. Okay, very good. That's what we're doing. That's what we're talking about. And we're applying these skills so we can take what we're learning and look for key features in a new situation. We're practicing learning and applying, where the stakes are just missing some points on a quiz. The stakes are low, so try that skill so that when you're out there and you need to fix something at your company, you know you can do it. You trust how you read the instructions and how you apply them in your situation. Thanks for watching.